So it's a pleasure for me to introduce Prof. Damani. He finished his PhD from Austin in 1999, and I think after working with the industry for a couple of years, he joined the School of IT, which was a separate entity, in 2004. So 2010 onwards, he's been working with the drinking water group in Sitara as well as in computer science, and so we through this group they've, I think, understood hundreds of water supply systems all over Maharashtra, and they've been analyzing their design and their provisioning. And I think from there came the motivation to actually design a tool which will help our engineers, field engineers, government agencies to improve their design process. So it's an innovation which is replacing some maybe about 40-year-old system called branch and loop, a DOS based system, and this is a more advanced GIS system. So it fills an important gap between a very rudimentary system and high end, very expensive licensed software. So it is actually satisfying the role of a public university in providing public goods in the design space for developmental areas. So I welcome Om to talk about JalTantra.
Thanks Milind for setting the stage, and thanks IRCC for giving me this opportunity to talk. Of course, like as Milind described, this work has carried out over a 7-8 year period with support from a large number of colleagues, students and contributors, and main contributors are all listed here, but other than that also there were others who joined the team at various points in time and worked for others. So some colleagues also asked me to talk about what does it take to work with government, how do you get our ideas being used by the government. So I will briefly talk about that also along with the technical details. But so one is in any real life issue we talk about, then the importance of interdisciplinarity comes. That technology solves a problem, but technology is embedded in a social context, a social, political, administrative context. And that context has to be understood if we want our system, our tools, our ideas to be used and deployed. So of course the interdisciplinarity comes from many sides. One is that I'm from CSC, and as far as JalTantra is concerned, Sitara has been a second home, and as you will see, and then Professor Asutosh Mahajan from IOR helped us with so many optimization issues. Professor Pradeep Kalbar from CU and his students have been working. So together, together with all the faculty, and of course Milind and Puru have been partner in this journey. So together, team of faculty member along with their students and collaborators have worked on this. And in real world, if you see at the bottom here, that we have worked with various NGO partners, I will talk about them. So water supply engineers from different government departments made lot of presentations to district collectors, CEOs and other bureaucrats like Secretary Water Supply Department, Maharashtra and others. Even politicians, so the local MLAs, MPs, ministers, water minister and chief minister's office we have interacted with, and state engineering colleges, because finally IIT Bombay can only do so much, and our vision is that each local engineering college should work on the local problem. And this mediation of these departments of IIT with this world outside has been possible through these two important innovations of Sitara. One is the TDSL, and every semester you get a call for TDSL project where the student can leave the campus boundary, go out, interact, study a real life problem and document it and analyze it. And technology and development solutions. So while this is a student driven initiative, for sustained effort you also need full-time project engineers who carry project engineers, managers, coordinators who carry out this work. So it is the mediation by TDSL and TDSC that the development research or the research at IIT Bombay can be taken out in real life with all these partners. So that's an important point, and since I am also one of the co-PI for TDSC, I will be happy to discuss with others as to how to take your ideas and work with the government departments. So this is what's the JalTantra, System for Design and Cost Optimization of Rural Water Network. So we are not looking at actually designing a particular module in the sense of a technical design, changing technical parameter, but among the set of available technology, among the set of available options, how to put together a system. So that's when we say design of a system, and along with GIS interface and lot of other manual processes. The system has been optimized end to end, and also automated. And these are two different things that I will talk about, so that lot of the common errors that happen have been taken out. The important point is cost optimization, not optimization of some physical property or other. Physical properties come in form of constraints of what's the minimum head that should be provided. So it's not a research tool in that sense, but tool to be used by engineers. So we started working on this when NGO Disha Kendra approached Sitara that there's a drinking water crisis and what can we do? We have geared out the collector already. How does IIT Bombay help us? So that's when the first TDSL project was started by Milind, and for this particular area, and since then we have taken a team of number of students and analyzed a large number of failed drinking water schemes in Thane and Raigad district, and through that we understood this vicious cycle, right? That once there is a technical problem in a system, the quality of service goes down. So some people start stopping to pay, maybe people at the tail end, people who are getting bad service, and then they pull out. Then so there's less revenue, which leads to less maintenance. So further technical problem, and once some people don't pay, then others, even if they are getting good service, they will not pay. They say, oh, others are not paying, why should I pay? And so it's all the way downhill from here. So we started engaging with the rural water supply engineers, and we said the one thing they said was there is a strict norm. So sometimes they design a scheme knowing that the scheme may have some problem, but because there is a strict per capita cost norm, they may cut corners to meet the norm and design the scheme knowing well that it may fail later on, or not knowing, but it may lead to that failure. And so the importance of the cost optimization came, that even if sometimes it's a 5%, 10%, whatever percent cost that you optimize, it makes a scheme from unviable to viable. And that's where our work started. And of course, then the other thing is that government has to follow a strict process. So, and sometimes those processes are frozen in time, but to get there, for them to adopt our system, we have to follow their process. We cannot say you are doing something wrong, at least not initially. So we studied the government process in great detail, understood which part is ad hoc, what are the limitations of their current design process. They were using old technology which could only work with a small size. System was giving non-optimal performance and all. And so we decided that we really need to build a new modern software which will both in design and optimization help, which will do both of them. So the problem to be solved was cost optimization of a multi-village piped water scheme. So there is a source in a river or a well, something where the water is treated. Then there is a main tank MBR where the water is after the treatment is kept. From there it goes to various villages, and the intermediate tank called elevated storage reservoir, and from there it goes to villages. So this is the system that we want to optimize, pick the right component. So what is given to us? So we assume that the source is given to us, that this WTP, water treatment, and MBR locations are out of scope of the JalTantra system as of now. The network layout, because usually it's along the road and all, so this is also, we assume this is fixed. And of course the set of villages to be included for a particular problem. We can explore over different combination of villages. So given this as the input, there is still a lot that is left to optimize. The main component is this pipe diameter that constitutes about 50% of the cost. So that's where traditionally they have been optimizing. These other things, they have not been optimizing earlier, but now it's possible with JalTantra, is that where should we locate this storage reservoir, what should be their size, which all villages should be connected to which reservoir, which earlier was done based on their intuition and experience, and then of course the pump size and the pump itself. So to solve this big problem, first we just focus on the pipe diameter, because that was the only thing they were doing at the time. The rest of the component they were doing manually. So we just said, okay, let's solve this problem. So main idea here is that given a network, each link can consist of multiple pipe diameters. And so you have an optimization choices where each diameter, the cost is known, and there is a pressure that there should be a minimum pressure at each of the point. And so there is optimization which says, and in general, a link can have multiple pipe diameter. So you get an optimal cost. So just a very brief history, that this has now been studied over 30, 40 years and hundreds of papers and hundreds of systems in some sense. Now the rural networks are typically branched because the sparsity, one village is far away from another. Where the urban networks are looped because there is no real free space in urban networks. So every possible path you want to lay down a pipe. So focus of the work that I present today is on branch network, but we are also working on loop network. And then, so there have been various paradigms, and this, because this problem, optimal problem, is essentially unsolvable even with today's resources, loop network have been either nature inspired heuristics or the other heuristics, so the technical name for them. So in all this work, the main point, if you look at even after 30-40 years of research, that they were only focused on pipe diameter problem, and either they were heuristics for general problem, or they assume continuous diameter instead of discrete diameter, or they assume that we will put only one link per diameter. So there is a formulation, this was a standard formulation that was being used at the time, and but one is we realized, I mean, in practice we know there is no need to restrict each link to one pipe, and it's known that optimally if the cost function is convex, then there will be at most 2 links per pipe. So we modified this thing, but now we have an integer linear program instead of a linear program, so the runtime became really slow, and system was taking just too long to run. So we thought harder, and we realized that in 30 years now these LP solvers have come a long way, and the CPUs are much faster, there is a lot of memory. So just the way you don't want to write assembly code at your own and you let the compiler do the optimization rather than you yourself doing the optimization. So similarly we said let the LP solver do the optimization, what people were trying to do hard. The important is to come up with a clear formulation that still makes it LP. So again, so we iterated over various formulation, came with something that was much faster. So anyway, this is just some details of how the earlier formulations were inefficient. And finally, we find that in this first cast system, so this is the branch was the tool that was used by all rural supply engineers. And you see even a network of 100 node could not be solved by them. Then some of the research models could solve, let's say 100 node network, but not 200. 1000 node network, so our system could solve this. So this was the first version of the JalTantra. It was a desktop system and was deployed. Engineers at Thane Water Supply started using it, and as we presented at various fora, the MJP is the, so there is again rural and urban water department. MJP is the urban water department. So from Nagpur he got very interested and he visited IIT just to interact with us. From Nagpur he came all the way, and then he got MJP Nagpur to start using it. They gave lot of suggestions. So that's the important point, that it was developed in partnership with government engineer, taking their feedback into account, because we could change the system as per their need. So they were also interested. And so anyway, till now it was being used for small schemes. When the NGO Kashtakari Sangathan approached us and there was this serious drinking water crisis in Mokhada Taluka, you see bulk of the Taluka was tanker fed villages, and they said government engineers says it's not really feasible to design this. And this is the area from where all our drinking water comes. So we explored some alternative design, found that the design space indeed exists, but the main problem was that it was a very tedious task. So now in a large network, again, if you can decide where should I put the tank, which village should be served by whom, what should be the pipe diameter, there is a huge combinatorial space explosion. There are 2 to the power m configurations possible, and so we said fine, we can't really do it manually. And I mean, we of course initially tried the manually, understood the process, and because that's what the engineers were doing. And then we extended JalTantra system by this ESR configuration choice. So the main point here is that either you suppose you have a single ESR serving the whole network, or you can have multiple ESR, in theory one at each demand node, and the optimal point will lie somewhere in between. So anyway, so there is some details on why this optimization spectrum exists, because the pipe cost behaves one way and the tank cost behaves another way, and so therefore since they behave in 2 different ways, the optimal point will lie somewhere in between. And so we decided to include this ESR in our optimization model. But what it really meant was now we have to optimize both primary and essentially each ESR breaks the network into 2 parts. And so the part from main tank to ESR is called primary network and other is secondary. Till now they were optimized separately, and that I guess the good reason was because this is a combinatorial explosion. So we simultaneously model both primary and secondary network, and so these are some of the technical details of what it means. So finally so we showed, for example, we designed one thing for Mokhada grid with 30 villages and 13 tanks. The optimal cost will come somewhere between these 2 extremes. Now price for incorporating this ESR is, of course, there was a significant performance degradation, because again we moved back to an ILP instead of LP. And a 200 network was now taking 24 hours, which was earlier only taking few minutes if we didn't have this. So anyway, so we had to, then it took us a lot of time to again optimize our models. It also required interacting with engineers to understand, but it's not just a mathematical optimization, but saying physically what it means. Can I represent it like this? can really this node can be served by that village or not. So that kind of interaction was needed, and then that translated into mathematical optimization. So whole bunch of improvements were done, and of course we showed that mathematically they are optimal, that when I change a set of equations, so this is the linear relaxation of this is indeed a subset of this, so this is a strict improvement, and so we did that, and finally we find that after these optimizations it has again come down to, so this is like 5 minutes, so for a 200 node network that was, so this was many months of effort, and then further optimizations were done, and finally so another order of magnitude improvement was obtained. So this is the sort of the model that's currently deployed, and this is the time that it takes. And then this was again, we presented various fora, and we presented it to in the Public Health Engineering Department, Rajasthan. And there they said, look, Maharashtra gravity fed network work, but Rajasthan is plain and pumping is needed all the time. So we had to incorporate pumping into this. So, but the point is, pumping is, of course, if the source is below the demand node, then the pumping will help. But even if the demand node is below the source, pumping can still help because the path is not a straight line. So you may have to go down and then come back up. So even in such a situation, the pumping can help. And so therefore, this is a model which is solvable without pumps, but the cost would be higher. And if we can put some pumps, then the cost would be lower. Of course, for operational reason, you may not want to put a pump because then you need an operator, you need a pumping schedule. So it may be okay to pay higher cost upfront. But point is, now you have an option. And in Rajasthan, of course, or in any plain lands, you don't have an option of not having the pumping. So all of that was done. So we show that with pumping, the cost may come down further. And we give all kind of yes and no, where pump can be put, cannot be put, where an ESR can. So all possible configuration options are given to engineers so that their intuition and their experience is still not rejected. They may restrict this subspace, that only explore this subspace. And from our intuition, or because land is not available or whatever, a lot of things can be ruled out. So, because that was important for the engineers to use the system, right? Our goal was that we should mimic their process, we should make it easy for them, never make anything hard for them, never deviate from what they were doing. So that was the important goal. And so we integrated this, and this is the current status. So in various, lot of towns with various, like I said, rural water supply, urban water supply engineers, we have held several workshops. Based on their feedback, a lot of improvements have been made. Currently, we estimate more than 300 engineers are using JalTantra every day. And now that it's part of the official curriculum of water supply engineer at this Maharashtra Training and Research Academy. So every year, 100 more engineers in Maharashtra are being trained. And beyond Maharashtra, Gujarat, Rajasthan, Haryana, Chhattisgarh, slowly the engineers have started using as they come and attend our QIP courses, CP courses and other things. And as part of Unnat Maharashtra Abhiyan, lot of state engineering colleges have been trained, and it's part of their curriculum in many places, and they have done design verification of local scheme. And TDSC that I mentioned, Technology Development Solution Cell, over 100 real life schemes have been analyzed. I have personally visited with the students over 50 schemes. This was of course many years back when we were trying to understand the space and the other thing. So it's a work in progress, and we are now working on the loop network, make more and more feature improvement in GIS system, disseminating to more and more places, and maybe extend to gas network. But to emphasize this role of TDSC, and that anybody else in the institute who have an idea, who like to take it to the government department, and that the TDSC Sitara can facilitate this interaction, where the IITB department and development research that happens through our student projects and all, and then TDSC can help it take it to the government, to other colleges and to other stakeholders like NGOs and CSR. So please do talk with me later on if you want. Thank you very much.